the differential equation for modeling population growth, and usually works pretty well for bacteria, things that are small, that have a large number of them. So the growth rate, so that's going to be the derivative, of bacteria is proportional to the bacterial population. And that's within reason, since there is a limited amount of food, right? For radioactive decay, you can always decay to, half of what you are. You can get closer and closer to zero. You can't have the bacteria reproduce until they cover the entire Earth, right? So an example of this is a milk carton with some milk in it. There's some bacteria, and over time, the bacteria will eat the milk and multiply. And the more bacteria in your milk, I think it's their excretions, the more sour the milk will be. So, learn something new every day. Here we go. So we have the growth rate. So that's going to be, I'm going to use P for the population of bacteria, so P of T. I'm going to say population of bacteria. All right. And I'm going to put that in grams. It's a little nicer to model it in grams. So, all right, so we have P dP dt, the derivative, is equal to, so it's proportional to the bacterial population, right? Proportional means proportionality constant. So the rate of growth of the bacteria is proportional to some number times the current population, P of T. All right, and in this case, we're also going to say that K is greater than 0, so the population is growing. Right, and if the population is growing, one of the reasons we want that, we also assume that P of T is greater than 0 for positive population. Right, you can't have a negative population of bacteria. And so then that would mean if K is positive and P is always positive, then the rate of change here is going to be a positive number. So this thing is always positive. Meaning, the number of bacteria is growing. Bacteria is increasing. All right, so let's go ahead and solve some example problems related to population growth.